Do you recall our previous discussion about CDP, the Cisco Discovery Protocol? We saw that if we were sitting on a Cisco Catalyst switch, we could see our directly attached neighbors. Maybe that neighbor was another switch, maybe it was a router, maybe it was a Cisco IP phone. Well, great news, as you would imagine, Cisco Discovery Protocol does run on our Cisco routers, and we can use it to see who is layer 2 adjacent to us. That's a key point, layer 2 adjacent. We don't even have to have IP addresses configured on our router interfaces to see our neighbor. We're communicating at layer 2. That's great news for troubleshooting because that means that I can have incorrect IP addressing between two neighbors, and I could still see that neighbor via CDP because I don't need correct IP addressing. That's a layer 3 thing. CDP is working down at layer 2. Let's take a look at the output of the show CDP neighbors command, and I can see that router R2 is layer 2 adjacent to R1 and R3. I can see that I go out of my interface, fast Ethernet 0/0, that's what R2 is saying. It goes out of fast Ethernet 0/0 to get up to router R1, and as we go into R1, we're going into router R1's fast Ethernet 0/1 interface. Router R2 is going out of its serial 1/0 interface to go into router R3's serial 1/0 interface. These are my neighbors. If I want to see more detail about a neighbor, I could say show CDP neighbor detail. Let's check out the neighbor R3. Even though it doesn't have to have an IP address, if it does, CDP is going to tell me its IP address. Its IP version 4 address and its IP version 6 address, as you can see. And there's the link local address. We can see more information about that neighbor, what kind of platform it is. We can see what version of Cisco iOS it's running. It's running some flavor of Cisco iOS 15.2. And we see that we're running CDP version 2, which is probably what you're going to be running. That's what you run by default. If you want to run version 1, you've got to go in and turn off version 2. That would rarely be done. And if I scroll down in this output, we can see information about router R1 as well. What if, though, I did not want to run CDP? Let's say that I am a service provider and I don't want to send my customers information about my router. I don't want them knowing what version of Cisco iOS I'm running. I don't want them to know what kind of platform I'm on. That could be a security risk. How do I turn off CDP? Well, a couple of ways. We could go into global configuration mode and say no CDP. Let's use some context-sensitive help. By the way, here's how you turn off CDP version 2. You say no CDP advertise -v2. But if we just want to turn it off, we could say no CDP run. And that would turn off CDP globally. That's one way of turning off CDP, but let's say that we wanted to be a bit more granular. Let's say that we just wanted to turn off CDP on a single interface, not the entire router. Let's turn it back on the router. Let's go into global configuration mode and say CDP run to turn it back on. And let's say that on router R2, I just want to turn it off to router R3. Let's pretend that's my customer. So let's turn off CDP advertisements going out of serial 1/0, but let's leave them on going out of fast Ethernet 0/0. Let's pretend that R1 is part of our network. We'll leave that on. To do that, we can go into interface configuration mode for serial 1/0, and we can say no CDP. Let's use context-sensitive help again, and we can see the option is no CDP enable. This is going to turn off CDP on that one interface. Let's end that, and it might take a little while to time out. Let's go over to router R3, and let's do a show CDP neighbor, and I can still see R2 because it's not timed out just yet. Let's take a closer look at R2. Let's do a show CDP neighbor detail, and let's see if we can see some sort of a countdown timer here. Yeah, the whole time is 135 seconds. Well, I'm not going to wait for over 2 minutes for this thing to time out, but it would eventually time out to the point where R1 would be able to see R2 as a neighbor because CDP is on globally on router R2, but it's off locally on serial 1/0. I'll tell you what, just to prove the point, what I'm going to do is I'll let the video pause for you, and I'll come back after this whole time has expired. I'll wait a couple of minutes, and we'll come back and we'll take a look at the output of the show CDP neighbors command on R3 and on R1. I've now waited for the whole time to expire. Let's once again on router R3 issue the command show CDP neighbors, and now R2 is nowhere to be found. It's timed out. However, if we go to R1, we should be able to see R2. Let's do a show CDP neighbors. R2 is there. What we did on R2, we just disabled CDP on one interface. And we also saw how to disable it globally if that's what we wanted to do. And this can really help us with troubleshooting because we don't have to have layer 3 connectivity to our neighbor to get information about our neighbor, and it can give us a sense as to whether or not that neighbor is reachable over the link. So CDP is a great tool in our tool belt when it comes to troubleshooting our routed and switched networks. Now that we understand some of the commands and techniques that we could use for troubleshooting our networks, and we understand some of the underlying technologies in play in the network, let's go through a troubleshooting case study. Here's the situation. Router R1 is not able to communicate with an IP address of 4.4.4.4. And we could pretend that that's a host on a remote network, but as you can see in the topology, it's actually a loopback interface on router R4. Let's get started by just confirming the issue. That's a big thing in troubleshooting. When a user reports to us that something is not working correctly, let's make sure that we understand exactly the issue so we're not misinterpreting the problem report, so that we don't think we've resolved the issue when the user still has the issue. Let's reproduce it if we can. Let's try to ping 4.4.4.4, and it looks like it's failing. We've personally seen the problem. Now we need to start trying to find what's going on. Well, we could try to trace the route to see how far we're getting. If I do a trace route to 4.4.4.4, I don't think we're going to get very far. You see that we're timing out before we even get to a next hop address. What this is suggesting to me is that this router R1, it has no clue how to get to that network. In other words, that network is probably not in the IP routing table. Let's break out of that trace route and let's do a show IP route to see if that network containing 4.4.4.4, let's see if that's in the IP routing table. No, it's not. Also notice that we don't have a default route. There is no gateway of last resort, so we don't really know where to go. We're not going anywhere. In a case like that, a troubleshooting technique that we often use is to follow the path. Let's go, looking at the topology, to the next router, and let's see if the next router can get to R4. From here, can I ping 4.4.4.4? No, it's failing here on R2 as well. And we'll do a quick check after the pings timeout to see if 4.4.4.4, which by the way is a network, it's a 32-bit network, but it only has this one IP address in it. Let's see if 4.4.4.4, let's see if it's in the IP routing table. We'll do a show IP route. It's not in R2's routing table. Okay, let's keep following the path. Let's go to R3 next. Can R3 ping 4.4.4.4? Yes, it can. Well, that's curious. R3 can ping it, but R1 cannot, R2 cannot. Let's take a look at router R3's routing table. Let's do a show IP route, and we do have an entry. We see that we can get to 4.4.4.4 via a next hop of 172.16.1.2. And it said we learned that via Ospf. Well, let's take a look at our Ospf neighbors. Let's say show IP Ospf neighbors. Well, that is strange. We only appear to have a neighborship with router R2. We don't have a neighborship with R4, but we're told that we learned that route via Ospf. What might be going on here is something just recently happened in the network, and this route has not yet timed out of the routing table. That's a possibility. I think we definitely have an issue, though, that we can address that's very clear right now, and that issue is R3 does not have an adjacency with R4, and it definitely needs one to propagate R4's information down to R2 and to R1. So let's try to figure out, first of all, why this adjacency is not up right now. Could it be that the link went down recently? And that's the reason we have this residual route that's still in R3's IP routing table? I don't know. Let's see if the interface is up. We can do a show IP interface brief command to see if fast Ethernet 0/0 is up. It is up. Of course, if I were plugged into a switch on my way to router R4, it would show that it was up, so that's not necessarily telling me a lot. Let's see if I can see R4 via CDP. If I do a show CDP neighbor, do I see R4? Yes, I do. Is it up right now, though? Let's just ping it. Can I ping 172.16.1.2? That's the fast Ethernet 0/0 interface on R4. If I can ping it, that means it's up right now. I'm not looking at old data. This is currently up if the ping works, and it does work. Wow. R4 is up, but I've not formed an adjacency. This means we need to start asking ourselves, what is preventing that OSPF adjacency from happening? Think back to your OSPF studies. What are some things that are required for an adjacency to form? Some things have to match up, don't they? We have to be in the same area, as an example. We want to make sure that one of these interfaces is not a passive interface where it's not sending out hello messages. So let's take a look at the OSPF router configuration on both of these routers. I'm going to do a show run, and to limit the output to just the OSPF configuration, I'm going to say pipe this to section. That's what the S stands for. Pipe this to the section of the config that begins with router OSPF. And we're just going to see that section from the output. And I'm saying router OSPF1, that's a locally significant process ID. That does not have to match on R4. And I'm using a very generic network statement to say I want all of my router interfaces to participate in OSPF, and I want those interfaces to all belong to area 0. Okay, that looks good. Let's do a show IP protocols to see more information. I don't see that any interface is passive. Just to double check, let's take a look at the Fast Ethernet 0/0 interface on R3. Nothing strange seems to be going on there. I didn't see any passive command under the router OSPF configuration. It really looks pretty good right there. Let's go to R4. On R4, let's do a show run pipe to section router OSPF. Again, the process ID is 1, even though they don't have to match. They just happen to match in this case. I'm saying I want all of my interfaces to participate in OSPF. All of the interfaces belong to area 0. If I do a show IP protocols, it looks like Fast Ethernet 0/0, along with all of my other interfaces, is being advertised. So what could be going on here? You might want to pause the video and think about, maybe you just want to write down on a piece of paper, what are some possibilities? What would prevent a neighborship from forming? These routers can reach one another. They're in the same area. One thing that could be causing a problem could be timers. Remember, the hello and dead timers need to match up. Do you remember the command to see those values? We can do a show IP OSPF interface followed by the interface identifier, Fast Ethernet 0/0. Let's check out the timers. Let's check out the OSPF network type. It says that we are a broadcast network type, which is the default for an Ethernet type of network. We see the hello timer is 10 seconds. That's the default. The dead timer is 40 seconds. That's the default. Let's go look on R3's Fast Ethernet 0/0 interface. Let's do a show IP OSPF interface Fast Ethernet 0/0. What do we have here? Well, we're a broadcast network type. The hello timer is 10 seconds. The dead timer is 40 seconds. So those match up. Something else that has to match up is the MTU size. Is something special going on with the MTU? Again, we took a look at the Fast Ethernet 0/0 interface, and I didn't see any sort of MTU command in there that would reset the MTU to a non-default size. We can check R4 though, just to make sure. On R4, let's take a look at Fast Ethernet 0/0. Nothing strange going on there. So what else could it be? We've got matching MTU sizes. We've got matching hello timers. We've got matching dead timers. We have physical connectivity between the devices. They can ping one another. The appropriate interfaces are participating in OSPF. And even though they belong to the same area, an adjacency is not forming. Sometimes when we get into a situation like this, we need to get deeper. We need to look at some more in-depth information. And this is a little bit dangerous, but I want you to be aware of another kind of troubleshooting command that we have. It's the debug command. There are many, many things that we can debug in our router. This is going to give us a very granular look at what's happening with different packets going through our router. The reason I say this is dangerous is any traffic being debugged, it's being handled by the router's processor, and that can really bog down the router. I've done that before. I have debugged too much information on a remote router one time, and it became unreachable over the IP WAN. I had to make the phone call of shame and ask somebody to go in and turn the router off and then turn the router back on to get access to it. You don't want to do unnecessary debugs. You want to be very granular in your debugging. And right now, it's clear that there's something up with OSPF. Let's do a debug IP OSPF, and let's use some context-sensitive help. How can we further fine-tune this? I'm thinking that looking at the hello messages might give me some more insight as to why this neighborship is not forming. Do I even receive hello messages from the other side? That would be valuable to know. Let's do a debug IP OSPF. Hello. And let's just wait to see if we receive any hello messages coming in from R3. If R3's Fast Ethernet 0/0 interface is participating in OSPF, we should, and indeed we are. It says we received a hello from 3.3.3.3. It's in area 0. There's its IP address. I want to stop the debugs. The way you stop a debug is to do a undebug all. That's one way of doing it. You can just, as a shortcut, say U space all. So you all will turn off the debugging. And we see that our dead timer is 40 seconds. The hello timer is 10 seconds. All that's matching up. And then we start to get a little bit of insight. Mismatched hello parameters. This is telling us something. It says that from router R3, the hello parameters coming in don't match up with what R4 believes should be in those hello messages. So let's go down that list again. We've got the same timers. We've got the same MTU. We're in the same area. There was another requirement though. Do you remember what it was? We've got to be on the same network. And you might say, well, obviously we are on the same network. We could ping one another. That doesn't necessarily mean that our networks completely match up. We still could have different subnet masks on those interfaces, and we would still have communication between one another, whether I had a 30-bit subnet mask, which is what we have on our topology diagram, or whether I had a 24-bit subnet mask. They could still talk to one another. Let's take a look. Let's do a show run, and let's take a look at the configuration for Fast Ethernet 0/0 on R4. We should have a 30-bit subnet mask, and we do, 255.255.255.252. Let's take a look at router R3. On router R3, we see it right here. Look at this, 255.255.255.0. That could be an issue right there. That is a 24-bit subnet mask. The other side of the link has a 30-bit subnet mask. Even though these routers can ping one another, technically they're on different subnets. Let's fix that. Let's go into interface Fast Ethernet 0/0 and let's say IP address 172.16.1.1 with a 30-bit subnet mask. And let's see if that changes anything. We'll wait for a second to see if we get any. Actually, we already did get an OSPF update. It said that we've gone to a full state. That tells me that I've formed an adjacency. Let's see who it is. Show IP Ospf Neighbors. Look at this. I have now formed an adjacency with router R4. Fantastic. As a result, I wonder if that network of 4.4.4.4, remember it's a 32-bit network, I wonder if that's been propagated down to R2 and down to R1. Let's go back over to R1 and see. Let's do a show IP route now that we fixed that. This looks promising. 4.4.4.4 is in our output. Can I ping it? Ping. 4.4.4.4. Yes, I can. I bet I can trace route to it as well. 4.4.4.4. And indeed I can. And again, the issue was we didn't meet the OSPF criterion of having all of our parameters match up. We've got to have the area that matches, the hello timer, the dead timer, the MTU, and the network has to match. And even though we could communicate between R3 and R4, we could ping one another, the subnet mask was different, and that was the issue.